Howdy. We are working on the project Transforming Reinforcement Learning, solving partially observable Markov decision processes with transformers. DQNs have proven to be effective in playing games, but the inputs are fully observable frames from the games. However, in the real world, we may not always have the complete state information available. Complex environments are often involved in real world reinforcement learning problems. In these complex environments, the agent receives only partial observations of the states, including noisy observations. However, achieving high performance in such cases is desired. In this project, our main goal is to learn the optimal policy in such space where we have limited observability of the environment. In order to perform well in such tasks, the agent needs to have access to past observations to build a more comprehensive understanding of the environment. While the usage of recurrent neural networks is wide to incorporate memory in reinforcement learning, they can be easily breakable and difficult to train as the overhead increases. This leads to failure in some cases. While RNNs and LSTMs are used for sequence modeling problems, they cannot handle long range dependencies. The performance of DQNs is poor in such partial observable situations. As the solution for these problems, we incorporated transformers which have shown to model sequences better than other models. They have the ability to capture long range dependencies since they incorporate self attention mechanism. They pay attention to the most relevant parts of the input sequences. This attention mechanism is of great help for partially observable environments. We, in our experiments, investigated that transformers solve the problems more effectively. Now, to give a little overview about our project before we go into the details, we have chosen two environments from the OpenAI Gym. One is Cardpole and the other one is Luna Lander. We formulated these problems as a POMDP problem by masking velocity components of the observation space. Then we implemented DQN and DRQN on these POMDP environments. These were our benchmark experiments and also our interim experiments. In the DRQN architecture, LSTM is used, but we have replaced LSTM with transformers. Then we compared the performances of our implemented models. Coming to the motivation, we know that for a POMDP environment, the agent requires memory. We add recurrency to introduce memory. Transformers are trending and they model sequential data better than LSTMs in DRQN. Transformers are great in capturing long range dependencies. Adaptation to different types of POMDP problems can be easily achieved by transformers. We found this experiment interesting for several reasons. First is that in the real world situations, the environment is complex and generally it is very difficult to get the full state observation. POMDPs more accurately represents the dynamics of the real world situations. It is also worth noting that POMDPs are quite challenging for RL algorithms to solve effectively. Hence, so many real world problems could be solved if the RL algorithms can solve POMDPs efficiently. Now, coming to the applications, our project currently focuses on solving partially observable classic environments such as Cardpole and Lunar Lander. This can be extended to solve POM-DPs in the real world. For instance, we can use it in autonomous driving where the roads are not clear, and that is the POM-DP problem. We can use it in finance to optimize trading strategies where the market is partially observable.
As mentioned previously, our aim is to use reinforcement learning techniques to solve a partially observable problem. We used two of the infamous simulators from OpenAI Gym, Lunar Lander and the Cartpole. In our project, we used our implementation to solve the partially observable Cartpole and Lunar Lander. Both problems are formulated as partially observable Markov decision process so that the state of the system is not completely visible. We have hidden some of the components of the observation space to formulate these problems as a POMDB problem. A general solution approach is to use deep reinforcement learning algorithm based on neural networks such as DQN or policy gradient. In our project, we have used the same scenario and improved the existing solution by solving the problem with transformers. For our first simulator, which is cart pole, a cart moves along the track and the pendulum is placed upright on the cart. The goal is to balance the pole by applying forces in the left and the right direction of the cart. The MDP formulation consists of the following. First is the observation space, which has four components: cart position, cart velocity, pole angle, and pole angular velocity. You can see the range of values that these components can take in the table. Next is the action space, where the cart can be pushed to either the left or the right. Since the goal is to keep the pole upright for as long as possible, a reward of +1 for every step taken, including the termination step, is allotted. We have implemented a partially observable case where we only consider the cart position and pole angle, hiding the velocity of the cart and the pole angular velocity from the agent. As seen in the table, the card position and pole angle are the only two that can be observed by the agent. For the second simulator, we worked on Lunar Lander. It is a classic rocket trajectory problem where the lander is supposed to land in between two flags. It has a state space of 8. The vectors include xy coordinates, linear velocities in x and y, angle, angular velocity, two booleans that represent whether each leg is in contact with the ground or not. The action space is 4, do nothing, fire left, right, and the main engine. The reward for this problem is diversified and the problem is considered solved when the reward is consistently above 200. The partial observability factor for this problem is again velocity masking, like the cardboard problem, but here it includes the linear velocity x and y and the angular velocity. We initially analyzed the performance of deep recurrent queue network on both the scenarios and later extended it to transformer based model. There has been a lot of interest in applying deep learning methods to solve problems in reinforcement learning. With the DQN to solve partially observable MDPs, it is required to keep track of the previous observation in order to do well on the task. However, this has certain challenges like the huge memory requirements that are required to keep track of the previous observation, so it is important to predict the value based on the current observation alone. This paper on DRQN by Matthew Hosnich and Peter Stone uses LSTM network to capture the long-term dependencies between the observations and not rely on using the previous observation with the current one for each time step. The deep recurrent Q-learning algorithm employs a recurrent neural network to model the temporal dependencies in the partial observable states of the environment. In terms of training, the difference in DRQN as compared to DQN are the way of sample generation. The samples are generated from the episodic memory and not the replay buffer like the DQN. This means that all the samples in the batch belong to the same episode. Here is the DRQN model architecture. In the left side is the image of the model architecture that is implemented in the DRQN paper that we saw previously. Their model consists of three CNN layers followed by LSTM network at the end. The CNN layers are useful for their application where the environments generate image based states. For our simulators, which is the Cartpole and the Lunar Lander, the states are in the form of numerical vectors. So we are using a model with linear layers instead of the convolution layers and LSTM layers to keep track of the temporal dynamics of the environment.
Here is the transformer architecture that we use for our problem setting. You may notice that this is the exact architecture that is being used in the encoder of the paper Attention is all you need. I'm going to explain what happens during the forward pass. We use the transformer in the context of reinforcement learning. So our input is a sequence of observations. The input sequence is sampled from the episodic memory. That is, each sequence has trajectories of a fixed length which are sampled from the agent's interactions with the environment. We then add sinusoidal positional encoding. This is to help the model understand the importance of the order of the observations in the input sequence. After adding the positional encoding, we then compute the attention scores within the input. The more details we'll see in the next slide. A very commonly used attention mechanism in transformers is called masked multi-headed attention. We use this attention mechanism in our architecture. After that, we pass the attention outputs to a multi-layer perceptron. This whole module consists of one layer of the transformer. We use n such layers and pass the final output through another MLP. This concludes the forward pass of our network. Now let's look at some of the details of the attention layer of the transformer. For each input X in the input sequence, we generate an embedding representation that takes into account the influence of other points in the sequence. To do this, we generate three vectors, namely Q, key, query, and value, which are computed for each input. Then we take a dot product for the query corresponding to the input with all the key vectors, which are then passed through a softmax layer to get the alpha scores for all the inputs. These alpha scores sum to 1 due to the softmax. These scores represent the attention values, which indicate how much the current input is influenced by others. Finally, we take a weighted sum of all the value vectors according to the attention scores, which gives us the embedding for the current input. Now let's look at our algorithm. We have two buffers. One is the episodic memory buffer M, which is used to store episodes, and other is the buffer B, which is consists of the transitions within a single episode. Like the DQN model, we have two networks. One is the Q value network, and other is the target network, which we initialize using random weights theta and theta prime. Uh, we run the algorithm for n iterations. Uh, for each iteration, we reset the buffer B. We then take actions according to the epsilon greedy policy, which uses the Q network, and we store the transitions in the buffer B. We continue this till the episode terminates. Once the episode terminates, we add the contents of the buffer B, which are the transitions observed in the episode, to the buffer M. If the buffer M now has enough episodes for us to start training, we then go ahead and train the Q network and the tau networks using the episodic data present in M. Finally, we also update the target networks with the.
Coming to experiments, the primary goal of our experiments is to investigate whether transformers can give better performance when dealing in POMDP environments. We consider DRQN as our baseline and design our experiments to compare transformers with the baseline. So far, we have conducted experiments on two environments, Cartpole and Lunar Lander, and compare their results and analyze their performance. We use different hyperparameters like number of layers in each environment, which leads to a slightly different network architecture. Next, we will look at hyperparameter details. We searched across hyperparameters of our interest and selected the best performing hyperparameter set, prioritizing performance for each environment. I will just give a brief description of what each hyperparameter is. N heads is the number of heads we use in masked multi-head self-attention layer. N layers is the number of transformer layers that we stack together. S is the number of observations in the input sequence that are being fed to the network. For example, in CardPoll, we use the sequences of length 20, which means 20 sequential observations sampled from an episode. LR is the learning rate. Batch size is self-explanatory. N is the number of epochs that we train the network for. TF is the target update frequency. It indicates how frequently the network's target network's parameters are replaced with value network parameters. M is the episodic memory buffer size. For example, 200,000 here indicates that the buffer only keeps the most recent 200,000 episodes. Optim is the optimizer we use for gradient descent, and we use Adam optimizer here. And embed is the dimensions that we project our input to. This dimension is retained throughout the transformer layers. Dropout is the dropout value we use as the regularizer for our network. Epsilon is the epsilon we use in our epsilon greedy policy while we train the network. In our experiments, we use linear annealing for epsilon, which starts at 0.1 and goes to 0.001 by the end of all epochs. These are the results that our best model has achieved on CardPoll environment. The plots show cumulative rewards obtained by the trained agents per episode. We can notice that the transformer network outperforms the baseline DRQN network on CardPoll. In this plot, we can see that at the 1200 episode mark, the transformer's reward converges around 325, whereas the baseline struggled to break past 200. We will now see a short video demonstrating the agent's performance. As you can see here, the agent keeps the pole upright for about 7 seconds. The agent's performance is expected as it is indicated by the rewards plot in the previous slide. These are the results that our best model has achieved on lunar lander environment. We can see that the transformer network marginally performs better than the baseline DRQN network. The transformer's best reward is around 150, whereas the baseline's best score is around 100. However, we can see that neither of these models achieved the minimum reward to be considered successful in lunar lander, which is around 200. Next, we will see a short demo on the agent's performance. As we can see, the agent takes a very long time to land. And even when it does land, it is mostly outside the flags. The reward plot already indicated this performance, but this video just reinforces the conclusion that the performance of transformers is desired level. Coming to conclusion, the results of these experiments indicate that the transformers performed better than DRQN on each of the environments, but the improvement in lunar lander is only marginal. Moreover, it did not perform on the level of expectation in lunar lander as evident by reward plot and the video demo. While this could be accounted to the fact that lunar lander is a more challenging environment than CardPoll with larger state space, but we also think that we did not reach the optimal model in our hyperparameter search. It could also be due to our architectural choices such as ReLU activation function and causally masked attention. Our choices are mostly derived from the working transformer models on NLP tasks, specifically text generation. Despite this, the results convinced us that the agent learns to interpret the missing state observations from memory. Theoretically, longer the sequence, the better the model should perform. In our case, since the missing observations are just velocities, the agent should not need drastically large sequence lengths. It would have been better to test our theory through ablation studies, but we will leave it for future work. Coming to future work, first of all, we would like to find out the hyperparameters that lead to convergence in lunar lander. We would also like to visualize the attention scores to see what history the agent refers to from its memory while making online decisions. Additionally, we would like to conduct a study on how does the sequence length affect the performance. Apart from the work we can do on existing model, we would also like to see how transformers work in challenging environments like grid environments with continuous space, and environments with different kinds of POMDP, such as flickering screens and noisy observations. The next slide gives a rough outline of the efforts of every individual in the team. Thank you.